Assalamu alaikum everyone. My name is Khadija Ali and my teammates are Mariam Nadeem and Noman Zafar. We will be presenting our discrete structure semester project titled Temporal and Category Based Price Similarity Network Analysis. In this project, we applied discrete structures, specifically graph theory and order theory, to analyze the economic connectivity of Pakistani cities. Our goal was to answer a simple question: do prices in one city behave like prices in another? And can we map the hidden structure of Pakistan's economy using only price data? For this purpose, we utilized Monthly Consumer Price Index CPI data from the Pakistan Bureau of Statistics. We processed data for two distinct years, that is 2023 and 2024, covering seven major categories ranging from food staples to transport. We mapped all products listed in the dataset onto seven different categories as shown on the screen. The challenge was to turn this raw data into a mathematical object. We did this by normalizing the data, mapping each category vector per city. This removed scale differences and made patterns comparable as the data started lying between 0 and 1 for each city. Next, we took out the cosine similarities by running Python scripts that used the pandas library. Through these scripts, we were able to take out the similarity matrices for each month, representing the similarity in CPIs among cities. We had one similarity matrix for each month as shown on the screen. This helped us model the relations and further graphing. Threshold controls sparsity. Lower threshold creates denser graphs. Higher threshold isolates only very similar cities. For our main results, we used a conservative threshold to emphasize strong structural links. We used the threshold to map our data onto graphs. Each city becomes a node, and each edge represents a relationship between cities. Edges are formed on the basis of the threshold. If a similarity is above the defined threshold, an edge is formed. Similarly, the size of the node represents how many edges it has. More edges mean bigger node. This converts our rows of numbers into a set of weighted, undirected graphs, one for each category, as shown on the screen. Now, Mariam will walk you through the next part of this project.
Okay, so to measure the economic importance, we treated all of the cities as nodes and calculated four specific centrality metrics using Python's NetworkX library. So I'll be going through all of the centralities that we targeted and what they actually meant in the context of our project. So starting off with the degree centrality, it just simply shows us the fact that how similar the prices are of one city to all of the other cities in that we targeted in our project through the data that we actually received from PBS. Then we have the closeness centrality, which is actually just a measure of how we calculate fast price shocks like inflation and how it can travel from city to rest of the network. Then we have the betweenness centrality, which is basically a measure of how uh, basically it identifies distinct economic clusters and the way they are bridging the gaps between them. And then we have the eigenvector centrality, which not only just tells us how many connections a city has, but it also tells us how who they are connected with. This is a snippet of one of from one of our codes that is showing how we use the NetworkX library of Python to calculate degree, closeness, and betweenness and eigenvector centralities. After that, after calculating all of the centralities, we faced a mathematical problem, which was that some of the data that we had was in a higher range as compared to some of the other centralities that we had. So in order for us to calculate all of the data in a fair manner, it was important for us to normalize it in a way that it can be treated equally. So after normalization, we brought all of the centralities that we had between 0 to 1, and that is how we and then further we used this data for our calculations and visualizations. This is one of the snippets from our Python code on how we actually normalize the centralities. After all of this, we were left with the question that which one of the metrics were actually important and which one of them were actually having a sort of impact on everything else. So instead of giving everything weights on our own and on our intuition, we used Shannon entropy, which works on a basic logic that if a metric gives everyone the same score, it's just noise, and if it varies, it has some form of information. And through this algorithm, we were able to, when we applied it on our data, the centralities we had, we were able to find out that the degree and eigenvector centralities had similar scores. So it was not given. They were very generic, so that was why they lost the unique factor. But the betweenness centrality was something that was unique and was given, and because of that, was given highest percentage. This proves that in Pakistan's economy, simple popularity doesn't matter. What matters is brokerage, which is basically just the ability to act as a bridge between the markets.
I'd now like to offer interpretations and explanations for our various visuals. First of all, our network graphs. What do our network graphs represent? Basically, the network graphs are working with CPI and the price change data. So they represent the price changes and how similar the price changes are within cities. The more denser the clusters and the more the edges, the more prices move in tandem, and the more similar price changes are. On the left, you can see the price change of transport in year one. You can see a very dense cluster. What does this mean? This could be due to transportation prices being federally regulated and government subsidies. Thus, the price changes are pretty uniform across the board. But on the right, fruits and vegetables have a lot more sparser network. They are a lot more independent and autonomous, if you could say that. Why is this? Well, the produce you buy is very much dependent on the local agricultural ecosystem, which puts a layer of disconnection between the prices between cities. Now, I'd like to explain the temporal relations. On the left, you have the aggregate prices of year one, and on the right, you have the aggregate price changes in year two. You can see a dense cluster in both of them, and tiny dots as well that are separate from the cluster. In year one, there are three dots, while in year two, there are two dots that are separate. These dots represent cities that are completely independent from the general price changes that happen and follow their own trends. On the left, those cities are Khuzdar, Larkana, and Banu, while on the right, they are Khuzdar and Banu. This indicates that Larkana has been integrated into the general price change ecosystem in the country. Now, I'd like to explain the heat maps. The heat maps represent our similarity matrices. The lighter the shade, the more similar the price changes are within between cities. On the left, you can see dark lines, vertical and horizontal lines that represent Khuzdar. This shows that Khuzdar is very independent from the trends from the rest of the city of the countries and from other cities. Peshawar is also a notable example, as it also has a darker shade, which represents a degree of independence from general trends and price changes from the rest of the country. But otherwise, in the year one, the heat map is dominated by lighter shade. This shows that clothing prices tend to move in tandem with the rest of the country in most cities. But there's a notable shift in the year two clothing heat map. It's a lot darker. What does this mean? This means that the clothing prices are now independent with other cities. Basically, every city's clothing is moving independent from each other. This could be due to several factors. This is corroborated by our network graphs. Year one clothing is a lot more denser, and thus prices move in tandem and are connected with each other. But in year two, you can see a lot of more distance, and the graph is a lot less denser. This showcases a degree of independence. Now, I'd like to talk about the trend in centrality. The higher the centrality, or the closer it is to one, the more similar it is. While the closer it is to zero, the more dissimilar it is, and the more disconnected it is. The cities we see for our graphs over here, uh, they could basically be shown in our previous examples as the nodes that move prices the most. If you zoom in some of our network graphs, these cities are usually the centers of the clusters. This means that they tend to drive price changes the most. Thank you.